next topic will be electric field. So we started with the electric charge. Now we'll go for electric field. So in that case, one second. Before we go for the topic, I'll just lower the volume was just. Once. Boys, can you are you able to see the slide? So are you able to see the video clipping?
Yes, ma'am.
Yes,
You can see, right? So just only one thing. 1 second. Just make sure that I include the video. So I'll just go for desktop. Okay.
It's time to learn the 5 rules of the electric field. The electric field is a force field that fills space, pushing and pulling on electrically charged objects. Rule number 1. Imagine this red ball is a large positive charge. Now we can test out the electric field with a small imaginary test charge. This is also positive. As I bring it nearby, you can feel the repulsion up close, a little weaker with distance. And on the other side, we also notice a repulsion, positive repelling positive in every direction. And that's all the first rule is. The arrows show the net force on a small, imaginary, positive test charge. Rule number 2. Electric field arrows point out of positive and into negative, out of positives and into negatives. But of course they do. That's the direction a positive test charge would be forced, out of positives and into negatives, out of positives and into negatives, out of positives and into negatives. These other far-off lines will just keep on going to oblivion. Rule number 3. Line density is field strength. That is, closer lines are together, the stronger the electric field. For example, if I add another positive charge to this glob of charge, it will increase the number of electric field lines, doubling the strength of the electric field. Now I want you to notice that the space between the lines increases. That is, the further away you get, the weaker the field is getting. If I add yet more charges, we have to add yet more electric field lines. You can witness the electric field in action when using a plasma ball. The electric field around a plasma ball is strong enough to ionize mercury, neon, helium, and even the air itself. Here, I'm helping the air get ionized with a conductor, a penny. But the effect weakens with distance. Rule number 4, electric field lines never cross. Imagine 2 positive charges. The net force on an imaginary test charge would be this and this. That is, two electric field lines. Crossing? No, no. The net force would be in the horizontal, as the two forces cancel in the vertical, leaving a resultant electric field horizontally to the right. Rule number 5. Electric field lines are perpendicular to the source and the terminal. That is, they always come out perpendicular to surfaces that are positive and enter perpendicular to the surfaces that are negative. Perpendicular at all times. This can be seen in these lettuce seed demonstrations. Soaked in vegetable oil are little lettuce seeds, and each side is getting charged oppositely. You'll notice the electric field is perpendicular to the conductors, even if the conductor is just a single point charge. Notice also that the electric field is 0 inside of this conductor. That is, there are no lettuce seeds moving. Review. As a review, consider these two charges, one positive and the other negative. This one's twice as charged as the other one. Now the lines must go out of positive and into negative, but the twice as charged one will get twice as many lines as the negative one. But the negative's lines will go into it. Now the electric field lines can never cross. So these ones have to travel to meet these ones. Notice that they're all exiting perpendicular. And now that you know these rules, you can draw any electric field. Good luck.
Okay, we'll start with the electric field, boss. So just were you able to hear the clipping? 12B?
Yes, ma'am.
Okay. So I'll just go for electric field. Can you see the slides first?
Yes, ma'am.
So we'll start with this electric field. Just write the statement. Now you should know what do you mean by electric field. So as what you have learned about magnetic field in grade 10, so we'll reintroduce that, then similarly you will be able to understand what is meant by an electric field. Suppose if I have a magnet, right, say a bar magnet, generally we say there is a region around the magnet, right, where the force due to the magnet can be felt. Suppose if I take two iron nails, nail 1 and nail 2. I'm taking two iron nails. One is placed within the field. The other one is placed outside the field. So this iron nail will not get disturbed. This is non-disturbed. But whereas the nail, which is inside the magnetic field, it experiences a force. So now generally what we conclude is that around any magnet, there is a region around it where the force due to the magnet can be felt. This is what we studied about magnetic field. And we very well know magnetic field are represented by magnetic field lines. Similarly, around any point charges, here you have a negative charge. Here you have a negative point charge. Here you have a positive point charge. Now look at this diagram. This is a continuous distribution of charges. Anyway, that we let us come back later. So now if you have a point charge, it can be a negative point charge or it can be a positive point charge. Now around any charge, electric charge, there is a region around any charge, and in this region the force due to the charge can be felt. Such region is called an electric field. So what is an electric field? Electric field is a region of space where a charged object experiences a force due to its charge, or I can say any body can experience a force due to a charge. So an electric field, you have to be very clear about it. The space surrounding an electric charge, right, has a property called an electric field. Now this electric field exerts a force on other electrically charged object. So if I have a charge, well, I'll go for an empty slide. The new terminologies are being introduced, you should understand. So suppose if I have a charge, a Q, right? Let us call this charge as a source charge. Now, this source charge is going to produce an electric field, a region around the charge where the force due to the charge can be felt, which means if I bring, say this is plus 10 coulomb. Suppose if I bring a charge of 2 coulomb inside this electric field, right? Now what is going to happen? Now this will exert a force. There will be a force of repulsion. Right, boys? Okay, if I bring a negative charge, say minus Q, say the charge of say minus 3 coulomb. Now this will experience a force of attraction. So these charges, whether it is plus 2 coulomb or minus 3 coulomb, now these charges will experience either a force of repulsion or a force of attraction only within the electric field created by the source charge. Is that clear, boys? 12B? 12B?
Yes, ma'am.
Yes,
Yes,
ma'am.
Okay. Please write the statement, boys.
Ma'am, though, so these fields, are they like infinite, or do they end?
No, boys, it is not infinite. It depends upon the magnitude of the
What
charge
do we
which is
write
created.
here?
Okay, so
Okay.
just write, boys. I'll give you the statement. I think for me, both the statement looks a slightly a different one. Just write the space surrounding an electric charge. Right, boys. The space surrounding an electric charge. The
Ma'am, should we
space.
write field lines also?
No, field lines. I'll give you next.
Right, ma'am.
The space surrounding an electric charge. The space surrounding an electric charge where other electrically charged objects experience a force or experiences a force is called an electric field. It's called an electric field. So what we can write is that the space surrounding an electric charge where other electrically charged objects experiences a force is called an electric field. Is that fine, boys? Now, how do you represent an electric field? An electric field is represented by electric field lines. Now, what do you mean by an electric field line? That will be the other question. So you know what is an electric field? Electric field is the space around any charge where the force due to the charge can be felt. That is an electric field. Now, how do you represent an electric field? Electric fields are represented by electric field lines. Represented by electric field lines. Now we'll go for what is meant by electric field line. Fine, boys. Shall I go for the next one?
Yes, ma'am.
Okay. So now, next is, now how will you define an electric field line? Your electric field, you represent it with electric field lines. Now, how do you define an electric field line? Now, suppose if I have a charge which creates an electric field, we call this charge as a source charge, right? Now, it creates an electric field. The electric field are represented by electric field is represented by electric field line. Now, what is electric field line? So suppose if I place a charge, say a small charge, we call this as a test charge. If I keep a charge plus Q near the source charge, now this will experience a repulsive force and begins to move. So the direction in which, or the path, I can say, the path in which, this is called a test charge, right? So the path in which this test charge is always a unit positive charge. Are you clear, boys? A test charge is always a unit positive charge. These two things have to be learned properly. This concept should be learned properly, because when you go for the reasoning and assertion based questions, these are the things which will be checked. So which is creating an electric field? A source charge is creating an electric field. Now, what is the next entity? It is a test charge. Generally, a test charge is a unit positive charge. Are you clear, boys? Are you clear? Will be,
Source charge have to be positive.
yeah, always, always. Why is that only Jonathan and only few boys are asking question? Okay. Now, I'll keep a unit positive charge, say at any point in the electric field. Now, what happens? This unit positive charge will experience a force and begins to move. This charge starts to move. The path along which the unit positive charge moves gives you the electric field line. So electric field line is nothing but the path taken by a unit positive charge placed in an electric field, and the direction in which it moves gives you the direction of the electric field. Shall I repeat? Shall I repeat? Even that I'm not getting any answer from
Yes, ma'am.
12B. Okay.
Ma'am, the definition you're gonna tell us, so we'll write it.
No, I'll read it. First, I have a charge. Say this can be 10 coulomb, whatever it is. Now this charge which creates an electric field, we call this as a source charge. So a charge which creates an electric field, we call it as a source charge, right? Now this electric field is represented by electric field lines. This is an electric field. So now this electric field is represented by electric field lines. Now your aim is to define what is an electric field line, right? What do you mean by electric field line? For that, let me place a test charge. A test charge is always a unit positive charge. It is always a unit positive charge. Okay, and one more consideration, if you check your NCERT textbook, it always states that the test charge will also create its own electric field. The electric field created by this test charge should not disturb the electric field created by the source charge. Now, if I keep this test charge, now this test charge will experience, this test charge is going to experience a force, right? And it begins to move. It begins to move. So the path along which the test charge moves is called an electric field line. So the path taken by a unit positive charge in an electric field is defined as an electric field line. The direction in which the test charge moves gives you the direction of the electric field. Is that fine? Is that fine?
Yes, ma'am.
Yes, ma'am.
Just write, boys. What is an electric field line? Just write. What is an electric field line? The path taken by. What is an electric field line? The path taken by a unit test charge. The path taken by a unit test charge placed in an electric field. The path taken by unit test charge placed in an electric field is defined as electric field line. Is defined as an electric field line.
Ma'am, can you repeat this one more time, ma'am?
The path taken by a unit positive charge in an electric field. The path taken by a unit positive charge in an electric field is defined as an electric field line.
Thank you, ma'am.
The direction in which it moves, gives the direction of the electric field. The direction in which it moves gives you the direction of the electric field. So what we'll do is, let us draw electric field. Electric field can be represented only by electric field lines. So let us draw electric field due to an isolated positive charge, isolated negative charge.
Ma'am,
Yes,
ma'am, what was that? The direction in which it moves?
Gives you the direction of the electric field. Direction of the electric field. Next comes electric field intensity, but before going for that, let me go for this, boys. Right? These are the 1 mark question. All of you should know in this chapter. If they ask a diagram based 1 mark question, this is the 1 mark question. Anyway, electric field, defining electric field line, everything is fine. Now, the electric field line due to a positive charge. Please do write. The heading is electric field line. So now it's all your diagram. Please, you are going to appear for your board exam next academic year. So all your diagrams should be taken into consideration, boys. So whenever you are drawing a diagram, as much as possible, use scale and pencil. So electric field lines, the first one is for isolated positive, only one single positive, isolated positive charge.
Your voice is
Oh, sorry.
breaking a bit.
It's fine now, boys. Is it fine? Because I'm just moving off the system. Is it fine?
Yes, ma'am.
Yes,
Okay.
ma'am.
So electric field lines, that is the main heading. First one is for an isolated positive charge. So now can you see there is a positive charge? Now this charge, we call it as a source charge. Yes, yes or no? Okay.
Yes, ma'am.
So now that creates an electric field. If I keep a small unit positive charge somewhere at one point, now that will experience a force. Suppose I keep it over here, experiences a force and moves. And the direction, sorry, the path in which it moves gives you the direction of your, this might be right. If I place it over here, moves, and that direction gives you the electric field line. So always it is radially outward. Can you see the arrows? Are you clear, boys? For unit positive charge, all your electric field lines are radially outward.
Ma'am, so you just draw this diagram.
You have to draw the diagram, but it should be symmetrical. Are you clear, boys?
Yes.
Okay. And it should, the arrows are very important because it is for a positive charge. what will happen if I keep a unit positive charge? That is your test charge over here. It will repel. So that's the thing. It's being, the arrows are pointing outward. And at every point, boys, at every point you can see the electric field line will be perpendicular. Is it not perpendicular to the surface? Is
Yes,
it
ma'am.
not? No, why? The reason is you have to draw a tangent. At this point, I have to draw a tangent because it's a spherical surface. Boys, suppose if I have a metallic plate, it is come right. This is called uniform charge distribution. Here, your electric field lines will be like this. Here, it's easy. You can see all your electric field lines are always perpendicular to the surface, right? Surface of the charge distribution. But since you have a circular one, the surface of the charge is spherical, then in that case, you have to go for, so I have to take a tangent. This will be. So that's the reason we say at every point. So this is for this, for a unit positive charge. Sorry, for a positive charge. What will be the electric field lines for a negative charge? So this is for isolated negative charge. Yes, boys. This is for an what happened? So here, if I keep a unit positive charge over here, now that naturally gets attracted. That is why the arrows are pointing towards the source charge. Anyone still have a doubt, boys, here? Arrows are important for, in the previous case, for a positive charge, all your arrows were pointing outward. For a negative charge, all your arrows are pointing inwards. Boys, once you have completed, just let me know.
Ma'am, only the diagram?
Only the diagram, don't write anything because it's self-explanatory, right? You know all the arrows are inward means what? The unit positive charge will experience an attractive force. Only the diagram was. Shall I go for the next one? Heading should be an isolated negative charge. Heading for this diagram should be isolated negative charge because you are drawing the electric field of an isolated negative charge. Yes or no? You are drawing, the diagram depicts the electric
ma'am.
field. Next, I'll go for a dipole. Now, you should know what is a dipole. Dipole will have, unlike charges, but the magnitudes are the same. Unlike charges, there is positive and negative, but equal magnitude. If this is plus 3 coulomb, this should be minus 3 coulomb. Right? So please do, no need for this statement, but
Ma'am, we'll just do the diagram.
diagram, but write the heading, was write the heading.
Now in brackets we'll write dipole.
No, unlike charges, yeah, you can write it. 1 second, boys, 1 second. There is a call coming. Sorry. Have you completed?
No, ma'am.
Only this one. Unlike charges, keep this in mind, boys. Always these are 1 mark questions. Right? In your board examination, you can always expect these diagrams as a 1 mark question. Right? These lines should be symmetrical. Arrows are very important. If you don't put the arrows, they'll cut the marks. So no need for these statements. Only the heading, which I have highlighted, and the diagram. Now, these combination of unlike charges of equal magnitude, we call them as a dipole. Aaron? Aaron?
Ma'am, could you repeat the name?
Whose name?
Ma'am, you're calling someone?
I called Aaron.
Okay.
I think I'm in 12B, right?
Yes, ma'am. Yes, ma'am.
Boys, you unlike grade 11, if you don't understand, please ask. Right? Otherwise, we will not be able to know whether you students have understood the concepts or not. You're just keeping quiet. Dipole is over. Shall I go for one more diagram, boys?
Sure, ma'am. You can move it.
Now look at this. Like charges of equal magnitude. Two positive charges of equal magnitude. Anyway, there will be a force of repulsion. Just write the heading. Like charges of equal magnitude.
Ma'am, does this also have a name like the previous one was dipole?
No, it's not. Especially dipole now becomes a very important concept over here, boys. Now, why dipoles are very why dipoles are very important concept is have you heard about polar molecules? Have you heard about polar molecules?
Yes, ma'am.
Oh, yes, ma'am.
Is it HCl polar?
Yes, ma'am.
Yes.
Yes, ma'am.
What else we have? This acetic acid polar. Is it polar?
Yes, ma'am.
Is water a polar? Water is a polar solvent, which means water
Yes,
molecule should be polar. What type of bond is water molecule will have?
Ma'am, hydrogen bond.
No, I just want in terms of either it is ionic or covalent. H plus and
Covalent, I think.
H plus and OH minus is covalent or
Sorry,
ionic.
ma'am. Ionic.
Ionic.
Ionic, okay. Any covalent compound, can you identify any covalent compound? Anyway, this I have to do when I come next chapter, last topic, polarization. Since you people were asking. Now, why dipoles are very important is that these polar molecules, whenever they are placed in an electric field, now how do they behave? That clear, boys? An electric dipole, if I keep like a bar magnet, if I place this bar magnet in a magnetic field, now how does it react, or whether it remains stationary or whether it experiences a force? See, Earth itself is a magnet, so Earth is creating a magnetic field. In this magnetic field, if I suspend a bar magnet, now in which direction the bar magnet, the moment I suspend, it will experience a force, and it orients along the direction of the Earth's magnetic field. The same way, when I have these polar molecules, when I put these polar molecules, right, boys, in an electric field, how does these polar molecules behave? Now, why this is very, very important is that all your chargers, what you use, your mobile chargers, they have a device called capacitors. Now, these capacitors are the devices which can store your electrical energy, and then they can also discharge the stored up energy. That is how, I don't know if you want to check, you call this as a variable capacitor or the cap. Now, the capacitance of the capacitor, suppose if you want your the device mobile to store more charges while charging, then the variable capacitors should have more storage capacity. So the capacity can be increased if I am putting a dielectric material. Generally, the dielectric material, generally we say it is a polar material which is a polar molecule. One video clipping was there, I don't know. Later on, when we come back for capacitance, we'll have more of these video clippings, so you'll understand things better. So that these are the applications of why you learn about your dipoles. Sorry, dipoles, that is especially dipoles. So here you have the chemistry and physics coming up together, right, boss? Fine, like charges of equal magnitude. Have you completed this? Then I'll go for the next one.
Yes, ma'am.
Yes, ma'am.
Uniform electric field between two parallel metal plates. Now, where generally this is a very important concept, because have you heard about CR? Now your television sets are LCDs, LCD screen. No? I'm asking you, boss.
Yes, ma'am.
Now, long back we used to have what we call it as picture tubes. Have you heard about these picture tubes?
No, ma'am.
No. This type of picture tube was
Yes, ma'am. The
old,
box.
old television sets used to have. Now all those things are being just replaced by LCD. Now in a picture tube, what is happening is that there is what we call it as a cathode, any metal for that matter. So this any metal in the form of a coil, like your tungsten filament. Now when you heat this metal, this metal surface will emit electrons. Now this stream of electrons will pass through like this two parallel metal plates, which means when they pass through the metal plates, they experience an electric field. So when they experience, so I'm asking you a question. Suppose I have a stream of positively charged particle passing through this. When the stream is passing along a straight line path, when it enters this charged plate, what will you notice? Will they move along the same straight line, or will their path be changed? If their path be changed, in which direction will they undergo a deflection? Boys, I'm talking about a stream of positive charge. Right? Positively charged particles are moving. Now there is an electric field between these two. These two are metal plates, boys. This is a metal plate. This is also another metal plate. Right? When the charged particles enter this metal plate, will the direction of motion changes? Will it go undisturbed, or will it get deflected? 12B.
Ma'am, it'll get deflected.
Who is answering? Siddharth.
Yes,
Siddharth,
ma'am.
right?
Yes, ma'am.
What about others in the class? Rishit, Shushal, Jopal.
Ma'am, it will get reflected.
It gets deflected. In which direction? Will it move upwards or will it move in the downward direction?
Downward direction.
Downward, yes, because it always gets attracted towards your negative plate. If it would have been negatively charged particle, if it would have been a stream of negatively charged particle,
I'm upward then.
upwards.
Upward.
Neutrally charged particle,
Straight.
straight, no deflection. Are you clear, boys? So this is what is happening. In a picture tube, you will have an electric field, you have magnetic field. So when these charged particles continuously move, they are deflected, and magnetic field will deflect in the other way. So what happens on your picture, on the screen, that is a fluorescent LED screen, these charged particles are continuously sprayed on the screen. That is what you get, those pixels. Continuously these charged particles will be scanned throughout the fluorescent screen, so the screen glows. So some other day when we have time, we'll go for, just it's out of syllabus, picture tube. If possible, we'll just go for it. Was anyone who wants to do a project on capacitors, if you can browse, but don't do it at home because safety is a concern. If you want to fabricate your own capacitor, you can fabricate. It's very easy to fabricate a capacitor, but at home, without your parents' supervision, don't do it. Right? Once the school reopens, so that reopens in that sense, when you people are back to school, if you have your practical session, please plan your project ahead, boys. Because once you plan your project, when you come for your practical session, you can do your project also. Okay.
Ma'am, are there any specific topics that we have to stick to when we are doing the project?
You want me to give all the topics? Shall I give the topics?
Ma'am, are there fixed topics or can we choose anything?
Anything, you can choose anything. I think I have given that C project. Did I upload it in your file section? No, right, boys? I will today. I'll upload. Just go for physics investigatory project. There are topics which I have given you the topics. For that, the laboratory will have a ready-made apparatus setup. Are you clear, boys?
All right, ma'am. Yeah.
Suppose you feel that you cannot go and browse and get material outside. There are ready-made apparatus setup in the lab. You can use those things and you can start doing your test.
But those are like those are examples, right? The topics we can choose our own topic.
Yeah, that's what. See, investigatory project. Nowhere teachers are supposed to force you. It is investigatory project. It should come from you. But we are just helping you out. Whatever you want to do, you just give me just at least in one page you write and send me. This is what I wanted to do. Do you have these setups in the lab? If we have certain components in the lab, I'll give you. I have one, but I don't know what.
Ma'am, it's a group work, right?
It's a group work. Boys, it can be a group, not more than 3 boys in a group. Maximum of 3. You can do it as your work as individual project also. Anything, whatever you want, it's up to you, boys. But the only thing is that don't start it at home, because if no one is supervising, it's difficult. So if you come to school, we are there. All precautionary measures can be taken in the lab. But now, please, this weekend, you finalize which group, but that should not go into the other class group. Your 11C boys are telling I'll do with 12B. Yeah.
Ma'am, 3 boys are maximum. If lesser than that's also okay.
Yeah, it's possible. Even one student, if you feel that, okay. Because your class looks like that. I think I can get more than one project. Single project in your class. You never speak up. 12B never speaks. You have your individual project, right? 12B. Sorry, 12B.
Ma'am, we still have to like decide who our team should be.
That
We
is
haven't like thought about the team yet.
Yeah, that's what I am telling. This weekend, talk about your team. Finalize your project. Finalize your team. I just want okay. This is what I'm doing. Can I have all these things? Because if you get me by the weekend, it'll take 1 more week because we do have CBSE board project starting. So we are focusing on it. Okay. Anyway, I'm just.
So should we email you about the topic?
Yeah, no problem, boys. You can do that. Okay. Fine, boys. Can we start with the properties of electric field lines, boys? Can we start with that? Can you write this? This properties are also very important. Why I'm saying in reasoning and assertion-based question, you can, please, whenever I'm stating something, boys, please do write sideways, right? Properties of electric field lines, just write r/a because you might get questions here. And boys, I have already posted in your physics file section yesterday in a folder called 12B physics. In that folder, if you go for a, what do you call, a file, I have given numericals, 4 numericals, I think 4 or 5.
What is r/a?
Reasoning and assertion.
We'll write all 4 of them.
Yes, you have to write. I'll read it out. Electric field lines will always originate from a positively charged object and terminate at negatively charged object. The previous diagram just check, boys. From in a dipole, how does the electric field line start? It starts from the positive charge and it ends at the negative charge. Is that correct? Correct
Yes.
or not?
Yes, ma'am.
Okay. Now, okay. What about here? Second one. The electric field lines originate and terminate perpendicular to the surface of a charged object. Suppose if
Yes,
I
ma'am,
have,
is correct.
so all the field lines are perpendicular. The density of the electric field lines. Now look at this. These two diagrams. In which case, I'm just marking diagram 1 and diagram 2. In which diagram the field lines, you have more number of field lines. Second one?
I mean, the second one, ma'am.
Yeah, so which means the density of the electric field lines indicate the strength of the electric field. More the electric field lines, more crowded the electric field lines, more will be the strength. And no two field lines from the same source can cross each other. And very important, your electric field lines do not form any closed loops. Very, very, very important. Are the magnetic field lines forming a closed loop? Are the magnetic field lines forming a closed loop? I'm asking you.
No, ma'am.
Yes, boys. Because what happens is your magnetic field line starts from North Pole, enters to the South Pole outside the magnet. But inside the magnet, they move from south to north. So they have a closed loop. But electrostatic field lines do not have any closed loop. So all these points, please do write. I think 3 more minutes, so I'll finish over here. So we started with defining an electric field. Then we started defining and what are electric field lines. Then we started drawing the electric field lines of an isolated positive negative charge of a dipole, and then 2 parallel plates. Now the last part what we have done is properties of electric field lines are over. Tomorrow, sorry, Sunday's class, I have to start with electric field intensity, the strength of the electric field. Very, very, very important concept, right? Then we have to do numerical on electric field strength. So this is how the chapter goes. So please, request from my side is that start practicing, boys. Start writing and practicing, and please complete the worksheet. What maximum I can do is that, boys, you complete the worksheet. If I'm not able to clarify it in class, I think I'll put a meeting and then a Teams meeting, then I'll go for. Should I invite some of you if I'm planning to do the worksheet in Teams meeting, or you people have your own classes, tuition classes, so that I'm not disturbing you? Okay, decide and put a message, boys. If you feel that the homework numericals, I have to sit with you in a Teams meeting after 6 o'clock anytime, just those boys, just put a message. Yes means then I'll be with some of these boys and I'll finish it off. The recorded version others can check. Okay, just decide and let me know. First write all these
Ma'am,
points.
that's for today.
Today, okay, fine.
Ma'am,
Today,
like if you finish, we can leave.
yeah, you can leave, boys. If you have completed, please do leave. Boys, you decide and tell me because I don't want to force. You have classes, so if you want me to be with you and complete the homework, that can be done only after school hours. For that, you just inform me whether Friday, Thursday, Saturday, whatever it is. Just inform me. Others, those who have completed, can leave.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank
You
you,
can all leave. Thank you, boys. You can all leave.
Thank you, ma'am.
Thank you, Prasanna.